Welcome to week 7. We're headed into the final stretch of the class. This video will cover chi-square, which is chapter 14 in your textbook, and then I'll post a follow-up video that tackles chapter 15, scale construction, reliability, and factor analysis. So this chi-square chapter in your book is a really short one. We're kind of ending on a high note. Chi-square is a pretty easy test to calculate, both by hand and in SPSS. So we'll cover the chi-square test for independence, which is discussed in your book chapter. And I also wanted to cover even a simpler version of the chi-square test, the chi-square goodness of fit test. So that one's not in your book, but I think it does kind of a nice job of providing a conceptual framework of what chi-square is and why we would want to use it. And it's a simpler version. So we'll start from that and we'll build our way up. So before we jump into the chi-square material, I wanted to recap a little bit where we've been in the class so far. So we started out talking about different types of variables and how we might measure them in different ways, whether they're nominal or categorical, ordinal, or interval ratio, which we also sometimes call continuous. And we said knowing how your variables are measured is really important, as well as being specific about what is your independent and dependent variable. So for example, in the correlation and regression unit, we used only interval ratio or continuous variables. And we talked about either correlation, testing an association between two continuous variables, or we talked about simple regression or multiple regression, making predictions about a continuous dependent variable based on one or more continuous predictors. So that was all interval ratio data we were working with. If you think back to our t-tests and our ANOVA, in that case, we were working with continuous dependent variables. So again, something we can take the mean of. But in that case, our independent variable was categorical, or it was something like a group membership. So looking at gender differences, looking at differences pre-test, post-test, a lot of different categorical independent variables we could use. So to finish off the course, we want to talk about what happens if you only have categorical variables. So in this unit, we won't be taking the mean of anything, but instead we'll be talking about categorical variables or frequency variables. So changing gears a little bit, and I think you'll find the calculations are a lot simpler because of that more simplistic way of measuring our variables. So this whole branch of tests that use categorical or nominal variables only are called non-parametric tests. So I just want to give you a little overview about what exactly they are. Ironically enough, why you should try to avoid using them if you can, but when it is okay to actually use them if you don't have a choice or if it's the test that best fits the data you have available. So again, if you think back to the very beginning of the course, we talked about different ways of measuring variables, and we said that there's a strength to using interval ratio data. For example, if you're talking about temperature of a specific city, it would make a lot of sense to talk about the average temperature rather than to classify it as hot versus very hot versus kind of hot, or to talk about a city as being the third hottest in the region, which would be an ordinal measurement. So we have a lot more power when we use interval ratio data. So our non-parametric tests are when we have categorical, or your book also discuss, there's a lot of variations of this using ordinal or rank data. However, when we use these non-parametric tests, it's a lot harder to use our confidence intervals and effect sizes. We have less statistical power, as I said, because we get a much more precise measurement of temperature by reporting it as a continuous variable than as a category. So that nominal and ordinal data classification provides less information. And at the end of the day, our interval data are always going to do a better job of explaining, therefore making a greater risk of making a type 2 error. So that takes us way back to the beginning of the course. So whenever possible, we prefer that interval ratio data, but sometimes we don't really have a choice. For example, a lot of times our dependent variable, it might be something that's actually nominal or categorical, or it could be an ordinal measurement. Also, sometimes when we have a small sample size and we might be working with a population that has skewed data, a non-parametric test might be a better fit. So if you recall towards the beginning of the class when we talked about the normal curve and the central limit theorem, one of the major assumptions underlying our statistical tests is that our data follow that normal bell-shaped curve. However, we know that that may not always translate into reality, especially if the thing that we're interested in is a category. So if you think about in education, a lot of times we might be interested in whether or not a student passes or fails a class, whether they persist in college or drop out, a yes, no. In healthcare, we might be interested in whether or not a patient develops a certain disease, a yes, no diagnosis. Whether someone lives or dies as a result of a procedure. So sometimes we do have variables, especially dependent variables, that are nominal. They might be that yes, no, that black or white answer. So that is a couple of ideas of when it's okay to use these non-parametric tests that rely solely on categorical or ordinal data. Chapter 14 in your textbook covers the chi-square test for independence. As I said a couple minutes ago, I wanted to take a step back and start with an even easier chi-square test, which is sometimes called a one-way chi-square or sometimes called the chi-square goodness of fit test. And I think this is a nice simple explanation of how a chi-square test works. So we use this when we have just one nominal or categorical variable. As soon as you add a second variable, that's when we must use the chi-square test for independence, which we'll get to in a couple minutes here. And really what we're looking for in a chi-square test is we're asking ourselves, how well do the data we observe fit with the data we would expect according to the null hypothesis? So if you recall back to our unit on hypothesis testing, the null hypothesis is always 0, no difference, there's nothing going on between our different groups. So in this case, if the data fit well, what we would expect according to the null hypothesis, if there's no difference, then we cannot or we would fail to reject the null hypothesis. So in a chi-square test, what we're actually looking for is a bad fit or a discrepancy into what we would expect, and that allows us to reject the null hypothesis. So I realize that that language gives you a little bit of a headache. So let's take a look at an example to kind of illustrate this point, this idea of good or bad fit. So a couple of assumptions with our chi-square goodness of fit test. Again, our variable has to be nominal. We would like each observation to be independent, so we're not surveying the same people multiple times. In a perfect world, we'd like to randomly select our participants. That might not always be possible though. And we want to strive for a minimum number of people in each category. And with this last assumption, there's a little bit of controversy, but I think kind of a good rule of thumb is you would like to have at least 5 sample observations in each condition. So it's kind of a timely topic, especially with young people, millennials, or even high school students. I think you hear a lot of times that younger people, younger generations are actually less interested in social media, or they're kind of moving on to different social medias. They're more into Snapchat than, say, Facebook or Twitter. So let's say for this study, we wanted to ask 100 high school students to indicate which platform they prefer, Facebook versus Twitter. And you can see here, I made up some data. I have 36 students who indicated they prefer Facebook, 64 indicated they prefer Twitter. So if we were to develop a null hypothesis around this research question, what kind of distribution would we expect to find under the null hypothesis? So if we had no evidence, no data, no background research, and we just asked 100 people, what's your preference? If there was no difference, we would just expect a 50-50 split. So we would expect 50 people to say they like Facebook, 50 people to say they like Twitter. So the question that the chi-square test is trying to answer is, how discrepant does that breakdown have to be in order for us to determine it's not a 50-50 split? So you can imagine if our distribution was 51 people for Facebook versus 49 for Twitter, that's pretty darn close to 50-50, and we'd probably say there's not really a preference. On the other hand, if it was 99 people for Facebook, 1 person for Twitter, we would feel pretty confident that there's a strong preference. And you can see here, though, we have a 36-64 split. So it looks like this particular sample is leaning towards Twitter, but again, how do we determine whether or not this is a statistically significant difference? Are these values discrepant enough in order to conclude that students in this case do prefer one social media platform over another? Keep in mind with this particular study, there's probably a couple of different ways we could have approached this. So we could have measured these variables in an interval ratio manner. We could have asked students to, on a scale of 1 to 10, how frequently or how much do they like Facebook, how much do they like Twitter. We could ask them to self-report in hours, how much time they spend on each platform, and that would allow us to use something like a t-test to compare their preference. But in this case, we kept it really simple and we just asked them, pick between these two, yes or no, put a check mark in one of these boxes. So we're really dealing with data that's measured using frequencies, or if you think of kind of a tally or a check mark, versus something that we would take the average of on a survey, for example. In chapter 14 in your book, there is a table labeled 14.5, and that has the chi-square formula to actually calculate this by hand. I went ahead and kind of spelled out what some of the symbols and words mean on it. But really we have chi-square equals, and you see there the Greek letter sigma, meaning the sum. And the numerator of our equation, we have the observed frequencies minus the expected frequencies, and then we've squared that difference, divided by the expected frequencies, and then again we would use the sigma and we would sum that. So the formula itself isn't too bad. You can do it by hand, you could do it like in Microsoft Excel, and it's even easier when we set it up in what we call a chi-square table. Here is an example of how we could set our data up using a chi-square table. So here on the far left-hand column, we have our 2 different categories, or our 2 different options on our survey, the Facebook versus Twitter. The next column, we have our observed, or the data we actually measured in our sample of 100 students, the 36 versus 64. The next column over, we have our expected frequencies based on our null hypothesis. And in this case, it's kind of that 50-50 split. So next, column over, we have the observed minus the expected. So you can see I just did 36 minus 50 to give me a negative 14. And similarly for the bottom row, 64 minus 50 to give me a positive 14. So the next step is to square those values. So taking both of these, squaring them, it removes the negative sign. So I end up with 196. Next, I want to take the 196, divide by the original expected frequency of 50. And you can see for Facebook, I end up with a 3.92. And same thing for Twitter, I have a 3.92. So if you recall, the last step was to sum those together using the sigma. And that gives us a sum of 7.84 for our chi-square calculated value. So our next question might be, how do we know if that's considered statistically significant? So that takes us to something we talked about kind of in the very beginning when we talked about the Z distribution and t-test, but we would want to look up and compare this calculated value to that critical cutoff. So there's a table in the back of your textbook that kind of lists out those critical chi-square values to determine the cutoffs, just like we did for the t-test. So to determine our chi-squared degrees of freedom, it's the number of categories we're dealing with, or K, minus 1. So in this case, I had 2 categories, Facebook and Twitter, so I end up with a 1 degree of freedom chi-square test. So you can see here, looking at the 0.05, which is kind of our default for this course, we end up with a critical cutoff of 3.841. And we would want to compare this critical cutoff to the value that we actually calculated, which if we go back a slide was 7.84. So in this case, that value of 7.84, if we were to graph it on the curve here, it's certainly exceeding that critical cutoff point. So we would reject the null hypothesis that there's no difference, that students have no preference among the social media platforms. And we'd want to go back to our original data and we could look at the frequencies and see that indeed students had a stronger preference for Twitter over Facebook. So to just go back to our chi-square table here, in that example, our expected frequencies we said was kind of a 50-50 split. I did want to point out that that might not always be the case. So maybe we have some previous research to suggest that students prefer one over another. Maybe our research says it's a 30-70 split or a 60-40 split. And all we would do is update those expected frequencies with whatever kind of previous knowledge we have and adjust our calculations. But in this particular example, with no other data available, we would just predict a 50-50 split. So we see that indeed there seems to be a strong preference for Twitter, at least among this group of students that we surveyed. So you can imagine the next question you might have is, well, there's probably multiple factors that play into that. How do I go about adding that and making a more complicated research question? And that's when we have two nominal variables. We are talking about a chi-square test of independence. So the calculations for this chi-square are actually very similar. They're the same. It's just a slightly more involved chi-square table to work through. And sometimes a little bit more work to obtain the expected frequencies rather than just assuming that 50-50 split. There is a good example in your textbook looking at gender differences in how college students select what major they choose to go into. So you can definitely look at that example in the text and kind of work your way through that. I have a slightly different example though that I wanted to kind of go through as an illustration. So in this case, this comes from a research study looking at a special state grant that was given out to first-generation college students. And the idea was that would this grant help first-generation college students persist in their college career and ultimately graduate? Will it help graduation rates? So you can see here, this table is broken down. We have our observed data. So we had 33 students who received a grant and went on to graduate, 18 students who did not receive a grant but went on to graduate. And then we have 60 students who got the grant and ended up not finishing, and 75 who did not receive the grant and also did not graduate. So you can see setting it up in a table like this kind of helps us keep straight which columns, which variables we're working with. So these are our observed frequencies. So if we wanted to kind of follow the same process as the first chi-square test, we'll need to get some expected frequencies in this case. Here at the top, I have again our observed data, and I've just gone through and done a little bit of math to sum across the different rows and columns. And we can use this data to obtain our expected frequencies. So again, if we had some kind of background data on college graduation rates or first generation college graduation rates, that would be really helpful here. But for the sake of this example, let's say that we don't have that information. And similarly, we would expect that graduating college is not necessarily a 50-50 chance. So we don't know what the expected frequencies are, but in this case, we're pretty sure using a 50-50 distribution is not going to work out either. So to get around that, we can use a little bit of math. For example, we can collapse across the rows and see how many people. We had 93 that received the grant, 93 that did not receive the grant, for a total of 186 participants. Likewise, if we look down the columns, out of our 186 people, we have 51 who graduated, and we had 135 who did not graduate. So not really great stats at this particular school, but this is the data that we have available to work with. If I ignore their grant status, whether or not they received the grant, and I simply look at those who graduated versus did not graduate, I can take that total and simply divide it by the total of number of participants in this study. So for example, if I take 51 graduates, divide it by 186, I end up with a 27.4% graduation rate. I could do the same thing with the people who didn't graduate, 135 divided by 186, or I could simply subtract the graduation rate from 100. So I would end up with 27.4% graduated, 72.6% did not graduate. So you can see here when I apply those percentages or proportions, the graduation versus non-graduation, I end up with an expected graduation of 25.5. We would expect that many to graduate versus 67.5 we would not expect to graduate, regardless of whether or not they received the grant. So hopefully that makes sense in terms of the math. Again, I'll show you how we can also do this in SPSS in just a minute here. So these are just kind of the steps that we'll go through. Again, with our null hypothesis, we expect there to be no difference between our graduation rates, regardless of whether or not they receive the grant funding. In terms of our degrees of freedom, it's a little bit more complicated. So we take the number of variables in our row, which again, we have grant versus no grant, -1, and then our column, graduation yes or no, -1. So we'd still end up with a 1 degree of freedom test in this case when we multiply those two together. We'd want to determine a critical chi-square cutoff, and we want to calculate our test chi-square just like we did before in order to determine whether we should reject or fail to reject our null hypothesis. So here you can see I've broken down that table a little bit differently. Instead of having kind of that row by column, I've listed everything down the column on the left-hand side. So the first condition are people who received the grant and graduated, who received the grant and did not graduate, who did not receive the grant but graduated, and who did not receive the grant and did not graduate. So if you go back a couple slides, you can see how I took that from kind of that 2 by 2 matrix and extended it out here into a slightly longer table. So my observed data has not changed. The expected is just like we previously calculated, and the rest of the process is exactly the same as the other chi-square test. So you can see here I took the observed versus expected frequencies and subtracted those. After subtracting those, I squared each of those values. And then after squaring those values, I divided by the original expected for that particular row. So if you remember then back to our equation, the final step is to sum that entire right-hand column. And you can see at the bottom there, that results in a calculated chi-square of 6.081. So in looking at our critical chi-square, again, it's a 1 degree of freedom test, so it's actually the same cutoff as our previous example, the Facebook versus Twitter example. Our critical chi-square cutoff, or our boundary, is 3.841. Our calculated chi-square value of 6.081, it's quite a ways out, it's exceeding that value. So in that case, we would reject the null hypothesis, and if we go back to our original raw data, we see that those who received the grant did graduate at a higher frequency than we would expect than those who did not receive the grant. But you can see overall our graduation rates are still fairly low. So this is a good example of how we might take that data and think about how we could further enhance it. Maybe it's not just the grant funding that determines it, but it's probably likely a combination of factors that contribute to student success and graduation. So this might give you a good starting point for figuring out how to extend the research and kind of further try to enhance those graduation rates for first-generation students. Even though the chi-square is pretty simple to calculate using that chi-square table, again, you could do it by hand or in Excel depending on how many cases you're working with. I wanted to walk you through here how we can run both that chi-square goodness of fit test in SPSS as well as the test for independence. So here are a couple of shortcut commands. I'll get SPSS booted up and we'll jump over to see how we can run these pretty quick and easy. I have SPSS open and I want to show you the way that I'll enter this data is a little bit different than what we've been doing. So there's a little bit of a process in order to set up our data correctly before we run our chi-square. So you can see in the bottom left that I'm on the variable view tab. It's highlighted in yellow, and you can see I'm going to enter my variables in this screen first. And you can see that for the first variable, row 1, I've named that platform. And in this case, I went ahead and clicked on that values label, and we'll say that 1 is Facebook, 2 is Twitter. Again, those labels don't really mean anything. I could have used 0 and 1. I could have used 2 and 4. It really doesn't matter. We just want to give them labels. So you can see here, I want to make sure to tell SPSS that I'm coding those with 1 and 2s. It's numeric. And in this case, the measure is nominal or categorical. For frequency, I'm just going to enter that in as a number. So it's numeric and it's scale, so that works great. So now I'm going to jump back to the data view, and you can see for platform here, if I enter 1, it's going to label it as Facebook. 2, it's going to label as Twitter. So we said before that in this hypothetical study, we had 100 participants. So if I were entering this by hand, I would go down and enter the number of people who picked Facebook, which I think we said was 36. So I would have 36 individuals that selected Facebook, 64 that selected Twitter, and I would have 100 rows of data. So instead of typing all of that out right now, I'm going to take a little bit of a shortcut using this frequency variable. So I'm going to go ahead and enter my frequencies here. So I think again for Facebook we said 36, for Twitter we said 64. So this is going to be a little bit of a shortcut. If I were to run it right now, SPSS is going to see this as only being 2 participants. But I can kind of trick it by going up to this data command and then going down here to weight cases. So the very last option on that menu. And all I'm going to do is select weight cases by and select that frequency variable and transport it over. So now when I hit OK, SPSS is going to pretend that in this data set, instead of just 2 participants, that I actually have 100, and they're divided between these categories based on the frequencies that I've inputted. So it's a little bit of a shortcut for the purpose of this example. Again, if you're doing this kind of by hand and actually entering survey data, you'd want to enter in 100 participants row by row. So now that we have our data set up, we're ready to run our chi-square goodness of fit test. So if we go under the Analyze menu, there's a whole menu called Non-Parametric Tests, and we'll actually go down to the bottom of this where it says Legacy Dialogues, and we'll highlight the chi-square one. It's the very first one on here. So there's a lot of tests under this non-parametric menu, but we're going to focus right now under Legacy Dialogue and chi-square. So once this dialog box pops up, it asks us for our test variable. So our test variable in this case is social media platform. Again, that frequency was just something that we use to weight our data and to create our data set. So the only other thing we have to do, you see here we have an option for expected values. And this is where you can see the default is all categories equal. So again, it's going to test that against a 50-50 split. If we had some expected frequencies or percentages we wanted to work with, we could highlight that values one and just enter those expected frequencies or proportions there. But because we expect a 50-50 distribution according to the null hypothesis, we don't really have to do anything else. So in this case, I'm just going to go ahead and hit OK since I've transported my test variable of social media platform. So you can see here in our output window, if you go up to the very top, you can see that SPSS turned on that weighting by frequency. And you can see that that is reflected here in our output because it thinks that there's 100 people in our study when we've really only entered basically 2 rows of data. So we see here our observed proportions of 36-64, the expected of 50-50. You can see that observed minus expected, it's calling it a residual, and that should look familiar. It matches the table that we did in our slides. And really our chi-square test is right down here. So our chi-square statistic is 7.840. It's a 1 degree of freedom test. And instead of looking that up and comparing to a critical chi-square value, SPSS has told us that that's significant at 0.005. So again, like all of our statistical tests, we want that significance level to be small, and specifically we'd like it to be less than 0.05, and in this case it is. So it's telling us that we have a significant preference in this sample for Twitter over Facebook. So again, it's running it very similarly to how we calculated it by hand, but it did it pretty quickly and easily in SPSS. So I'm going to go ahead and open a new data window, and let's take a look at how we can run the chi-square test for independence in SPSS. Okay, I went ahead and opened a new SPSS window, and I've put in our data again from this example in the slides with the first generation college student grant and graduation rates. So here I've entered grant, and I went ahead under the values column. I labeled whether or not they received a grant, with 0 meaning no, they did not, 1 meaning yes, they did. Again, the labels don't matter. You can make whatever numbers you want. Same thing with graduation. So 0 indicates they did not graduate, 1 equals yes, they did graduate. I've identified both of those as nominal measures, and again, I have frequencies as just a scale. So to set this up in the data view, again, I could go through and enter this for all of the people in the entire data set, but I'm going to choose to use that frequency shortcut again. So the first thing that I need to do is set up kind of these basic codes. So if we have no, they did not receive a grant, and no, they didn't graduate, they would have a 0 in both those columns. No, they didn't receive a grant, but yes, they did indeed graduate. And then similarly, yes, they received a grant, yes, they graduated, or yes, they received a grant, and no, they did not graduate. So we kind of have to keep our columns and frequencies and rows, all of that good stuff straight, and make sure that we're entering our data accurately, but this frequency column is going to help us out. So I'm going to go ahead and fill in that data based on what we had in our slides. So I went ahead and just entered that data from the table back in the slides, and I just want to be sure that I tell SPSS again to weight those cases by frequency. So exact same process as before. I do the weight by frequency, and in my output, it's telling me that that command is turned on. Now that we have our data set up, we can go ahead and run our chi-square test for independence. So this is where it gets a little tricky because SPSS does not put all of the chi-square tests under the same menu. So in this case, I'm going to go to the Analyze menu, and instead of non-parametrics, this is the weird one. It's under Descriptive Statistics, and this menu called Crosstabs. And basically what this is going to do is it's going to set up a table very similar to that we did in the slides. So I'm going to tell SPSS to put grant in the row, graduation in the column. It's going to know to include the frequencies because we weighted our data. Under this button called Statistics, this is where we actually have to ask for the chi-square. So I'm just going to check that box and hit Continue. And then let's see what's under this button called Cells. You can see that the default is to give us the observed. I'm going to go ahead and ask it to give us the expected as well, so we can try to make it look as similar to our example from the lecture slides as possible. And I'll hit Continue and then OK. So here we have our output. It's telling us the total number of participants. We had 186 people. We didn't have any missing data, so that's great. And then it's going to give us kind of this cross-tabulation table where we have the different conditions, the expected count versus what we've actually observed. So again, if you go back to the slides, this should look incredibly familiar to exactly how we did this by hand. But what we're ultimately interested in is the chi-square test. So you can see here, it's this first row, it's the Pearson chi-squared. And again, this value should look familiar, the 6.078. It's a 1 degree of freedom test, and here we know that it's significant at a level of 0.014, which is less than 0.05. So again, we're seeing a significant chi-square. Our observed frequencies are significantly different than what we would have expected given a null hypothesis. So that just gives you an overview on how you can run these two different chi-square tests. Again, if you were entering the raw data, you would have many more rows. I just took that shortcut in weighting the data by frequency in order to cut down on kind of the data entry time.